The presentation begins pretty in a straightforward manner. So I have someone here joining me, this person. Okay, maybe some of you guys recognize him. This person is Waldo. Okay, and here he is. And Waldo is a character in a child book or a popular book in which he lives among his friends and in various habitats. And the challenge is you need to find Waldo. And Waldo is known around the world by different names. In Italy, he's called Ubaldo. In Lithuania, he's called Jonas. In the UK, he's called Wally. And in Vietnam, he's called Van Lang. And the thing is, we always need to find him, okay? He's quite easy to find when the page is blank, like you see before you, okay? But he often, like all of us, live in different environments and like to do fun stuff. So what we need to do is find him. And sometimes Waldo likes to go to space. And so here's Waldo on the lunar surface. And what I like to do is set a timer, basically a 30-second timer, and ask you to find him. Okay, so here's the timer. You'll see a bar progressing across the top of your screen, hopefully. It's green. And you have about 30 seconds to find him. If you can find him, I guess the cool thing with Zoom is you might be able to annotate my slide. So if you find him, circle him. If not, I'll just ask if anyone found him in just a few seconds. All right, did anyone find him? You could raise your hand or clap or not say anything if you can't find him. Okay, John.
I think I found him.
Where is he?
So so on that little dome, he's in the second level.
Oh, right here.
Yeah, right there.
Okay, let's see. I think you're right. Is that where you were looking?
Yeah, that's where I was looking.
Okay, awesome. You found him very fast. Very good. So here's Waldo. We found him. And there he is. Okay. Someone found Waldo. Maybe there's another Waldo down here. Someone circled him in blue down here. Let's see. So that's what I'm going to talk about. Let me clear these annotations. There we go. And so the title of the talk is Here's Waldo, a virtual materials search, design, and discovery. And this is really what my group focuses on. We try to think about picoscale design. So that's setting the length scale of the design problem. Probably in some of the other talks, you've heard about people thinking of, designing materials at the microstructure level, the macroscopic level, if they're thinking about devices and connecting that to some functionality. It could be a battery material, a solar absorber for a photovoltaic device, etc. And again, in my group, what we're thinking about and trying to learn more about is how to design materials with specific electronic functions. I'll try to define that a little more at the picoscale. So trying to control how atoms are arranged. And this is all done in solid state materials, transition metal compounds. This is the class of materials I'm interested in. And so what I'm going to go through in this talk is how we think about this search and design process and how it can lead to real materials discovery. And maybe you're doing some avenue, some different versions of this in your own projects, whether it's an RU project or an RET project. So that's really the focus. So the first half of this talk is a bit light in the spirit, trying to tell you about how I think about this problem. And remember, this is my view on materials search, design, and discovery. There's no sort of unique, correct, single answer of what this really means. And then I'll show you how we apply it in the design of new materials. And this material that just popped up on the upper right-hand corner of the slide, this thing, is a solid state material. It takes the rutile structure. So if you're familiar with ceramic materials, this is the rutile crystal structure. And the interesting thing that I'll talk about is this compound has two different anions in it. So it has both oxygen and nitrogen. And the material you see up here was designed by an REU student in 2018. And this work, ultimately, he published in Physical Review Letters. And so this is the project that I'm going to tell you about towards the end of the presentation. Okay. So let's focus first now on the virtual materials search. So let's think about this problem. And the reason material searching works is in part because materials are very similar to human faces in the sense that all human faces share very common features, right? Everyone has a nose and eyes, ears, a mouth, etc. And so although they're all quite different, everyone has these features. And there could be or may not be some underlying mathematical structure to our faces. So we can discuss or debate that question. And just like in the Waldo search, there are optimal search strategies in material science. And so let's go back to the example with Waldo for a second. So when we're looking for Waldo, I can ask you guys, how did you find him? Or what did you do to find him? So Johnny, you were the first one who shouted out you found him. What did you do to search for Waldo, if you don't mind unmuting yourself?
Well, I kind of started from the top and I just scanned from left to right. And then
Okay, so you scanned left to right. Did anyone else pursue a different strategy that wants to share? You don't have to share.
I looked for the striped shirt.
You look for the striped shirt. Good. Anyone else? Okay, good. And so let's see. These are the most common strategies. Spot Waldo's clothes. So search for the striped shirt and his hat. Focus on landmarks. This is actually a very common search strategy you might want to implement. That Waldo doesn't just hang out anywhere. He likes to go to certain places and have fun, maybe like you guys. Similarly, materials we'll see like to hang out in certain areas, at least if they have a particular functionality. And then the other sort of search strategy is to know where Waldo isn't typically found. And Waldo is almost never spotted in the page's top left-hand corner. So if you're, have a cousin or a niece or a nephew and you're playing with them, you may want to reveal these sort of tricks to them. In a similar way, not all material functionality or properties can exist in any material class or in any material structure. And so knowing where to find Waldo, just like knowing where to find certain materials, it's as important to know where not to look. Okay, and this can help in the design or search of new materials. So we can translate this into material science language if we want, that if we're looking for Waldo's clothes, we can think about material structure. And when we're searching in terms of materials, we can search atomic structures, we can search microstructures, et cetera, and correlate that to physical properties. The type of search I'm going to tell you about is using local structure. And the compounds I'm interested in, again, are these transition metal materials. They're comprised of metal, ligand, or anion coordination polyhedra. So these you've probably seen in chemistry before. And when these units all link up together to tile space, that creates a crystalline material. Okay, and the way these structures or these units tile space and are connected give rise to electronic properties in transition metal compounds. And that's what I'm highlighting in this part of the slide, that if I change the way this unit, this is an octahedra, I can put a cation in the middle and anions on the corners, and I can take this unit and tile it in 3 dimensions. So I connect all the octahedra by their corners, or I can connect the octahedra by edges and stack them together. This is the same unit, but these two materials will fundamentally have different physical properties, even if they have the same chemistry, meaning I put nickel in this octahedra. These two materials will be very, very different. Okay, and that's this relationship between local structure or atomic structure that I'll try to emphasize in the design of a new material. Okay, and this gives rise to changes in electronic structure. So this is a spaghetti diagram for you. Again, I'm a computational materials scientist. The thing we study the most in materials is the distribution of electrons. And what you're looking at is energy of an electron as a function of momentum space. Okay, so the reciprocal lattice, not the real space lattice. And it's this distribution of electrons in momentum space that ultimately governs physical properties of all materials, all crystalline materials at least. And so this is what we'll discuss in some detail, not extensively, because I'm not sure how many people have thoroughly discussed electronic structure, but probably the majority of you know what the difference between a metal and an insulator is when you think of valence bands and conduction bands and some harmonic or single electron approximation that you've discussed in perhaps like a semiconductor class or a elementary quantum mechanics class. Okay, so that we can do search by material structure. That's what I just mentioned. We can also search by chemistry and chemical composition. And really what that means is going to the periodic table and saying, look, I want a material maybe that has, for example, calcium in it for whatever reason and titanium, or I want an organic material that has carbon and oxygen in it, something like that. And we can do searches this way, where we change the elements that comprise my chemical formula. So maybe I keep oxygen, but I can use a different chalcogenide. Those are elements in this row, or this column, sorry, here. And then I can choose, you know, my A site cation could be magnesium, or my B site could be manganese or iron, et cetera. And so we can make material searches just by composition. If we know like the end product needs to be a lightweight alloy, I need to use, you know, metals that are at the top part of the periodic table rather than refractory elements. Okay, so we can do searches in this sense. And we can also search by something here I'm calling a structure property contraindication. So just like we know Waldo often doesn't appear in particular spots, there are many properties which will not coexist in materials. And the only way to make them coexist is to find sort of a way to circumvent the incompatibility. And a well-known example of a contraindicated set of properties is a material which would be conducting. You know, it allows for an electrical current to pass, but is also transparent. So most of the electrical conductors you know of, metals, copper, aluminum, silver, are shiny and opaque. Things that are transparent, like the window glass, maybe just, you know, in the room you're looking at, or your display, tend not to be tend not to be conducting unless something magically is done. And magically means really engineered to be conducting. And so that's an example of contraindicated properties. Metallicity and transparency tend not to coexist. But as material scientists and engineers, we've determined ways to make them coexist. And so you can do searches in terms of material properties by these contraindications when you're looking for design. And so that leads then to the search for properties. And really a material property is something that connects a stimulus to the response you observe in a material. And these are the structure property relationships I'm going to talk about, and it will be in the context of, I'll tell you in more detail about a metal to insulator transition. So this will be a material that can transform its electrical conductivity from being metallic to being insulating. And this is useful for a variety of microelectronic devices. Okay, so this is the concept of virtual materials search. And this has been pursued in a number of ways today, often without direct experimentation. So probably many of you are doing or are trying to do or have done experiments in the lab before. A lot of material search today can be done virtually, and probably a fraction of you are doing such things in your research experience. And one of the strategies that have augmented virtual materials search has been the ability to do high throughput computational materials design. And this is sort of in the framework of doing, you know, not 10 to 20 calculations of some type, but doing hundreds to thousands of calculations where you compute properties or the structure of materials, and then you down select or filter from that set of results. And this was initiated in the early teens and has continued today. And some of the efforts in this material search has now more recently been augmented by advances in, I'll just say broadly, artificial intelligence. And artificial intelligence is just the science of making things smart. So it's human intelligence exhibited by machines, and a subcategory of artificial intelligence is machine learning. And I don't know if anyone is doing that in the research projects, but machine learning is an approach to achieve artificial intelligence in such a way that you learn patterns in data. And with those patterns, you can then make informed decisions and design or discover new materials. And so material search has been augmented by the ability to have this data infrastructure. So all of these high throughput calculations of some type gives rise to data, and then we can use methods from other communities, computer science, optimization theory, statistics, to then filter away materials that we're not interested in because they don't meet criteria for a particular design. Maybe we want a high temperature superconductor, or we want a mechanically stiff material or a hard material or a ductile material, and we can then filter that way. So some of these data infrastructures have really been advancing globally. There's a few in the United States. The top row is the Materials Project, which is led by Kristen Pearson. We have the Open Quantum Materials Database here, which is led by Chris Wolverton, who's a faculty member, also in material science at Northwestern. And then there's this A-Flow library, which is led by Stefano Cutarolo at Duke University. And then there's two initiatives in Europe that are happening as well. And so these are resources that you as students can access and find many, many thousands, hundreds of thousands of calculations that have been performed on compounds, and essentially they're just waiting to be filtered in some way, and you need to search for something in terms of the property or structure that you're interested in. So these are available, and this is the material search approach. And so what I want to shift to is then design. So does anyone have any questions about sort of this general view of material search before I shift focus to design?
Yeah, so everyone has to agree to store their electronic structure in the very same formats, I guess?
So in these 5 repositories, they are stored in some way. I think almost all of them use a similar format for the data infrastructure, these JSON libraries. But yeah, that is something that took time to agree upon, and that has happened. Some things like atomic structures, there are standards already because of practices of communities of physicists and chemists. So the chemistry community formalizes the way structures are stored both for organic and inorganic compounds, and those are codified in the IUPAC, I guess, library, which gets reviewed every 10 to 15 years. And so those types of formats are simply adopted. The manner in which data computed from an electronic structure calculation is stored can vary a little bit, but everything on these 5 repositories is downloadable. And so you can read it. It's human readable in that sense.
Is it just energy versus momentum that's stored, or something about the wave function is also in there?
It varies by repository you see here, and some repositories have more energy. Some repositories have things like more properties of materials, elastic moduli, dispersion curves for phonons, things like that. It varies. None of them are exactly the same. There is some information that's shared between some repositories. And then some have functionalities like this one in Nomad. They have built-in machine learning tools. So you can use a GUI to do machine learning with their data. And so OQMD has no machine learning tools implemented in their database, but you could download the data and port it over to Nomad if you want and use their tools. So there is an ability to communicate between repositories.
Thanks.
Good. Any other questions? Okay, so we'll, let me continue. So I'm gonna shift now to design and tell you a bit how I think about design. And virtual materials design, in my perspective, works because materials often behave more like numbers than faces. So let me just clarify really what I mean there. And what I mean is that the structure is well defined, and I'll try to further define structure for you. But just like numbers, the structure of numbers is very well defined, and it's what really permits us to classify numbers and do abstraction with numbers. And so here is a set of numbers. I don't know if anyone wants to shout it out. What are these sets of numbers on the left?
Even numbers.
Yeah, this is not a trick question. They are even numbers, you are correct. And then these are the odd numbers, right? These are the prime numbers. These are fractions. And then we have irrational numbers. And I don't have to enumerate every number for you to understand what the even set of numbers are, or the odd set, or the prime set, or the set of fractions, or the set of irrational numbers. And we know how to abstract these numbers as well. And for me, virtual materials design for discovery relies on having that underlying mathematical structure to materials. It's just that the fact that when we design materials, it's likely not always apparent that the underlying structure is highly mathematical. And the problem is that when we do this abstraction, or in fact, the underlying structure itself, it's just highly nonlinear. It's not a standard number line. We can't just count left or right on a number line and get to any number in the spectrum. But there is an underlying mathematical structure. And so when we do this abstraction, or when we think about the structure of materials, we have to make a similar abstraction that we do when we talk about numbers. So 3 can be abstractly mapped into anything, right? So it's almost lunchtime. So I can take 3 $5 bills and abstract that onto 3 Chicago-style hot dogs you might enjoy if you were on campus. And I can translate that or map that onto 3 bottles of Coke, which you might enjoy with your lunch. Okay, this is the process of abstraction. You recognize that there's 3 of each of these, right? Even though the quantity itself is quite different. In material science, or in the terms of the structure of materials, we can make a similar abstraction. So here, for example, on the left is just elemental niobium. So it's this shiny silver colored material. And this material is superconducting. It's a trivial, low temperature superconductor, meaning it obeys a set of equations known as the BCS gap equation here on the right, which won Bardeen, Cooper, and Schrieffer a Nobel Prize for their theory. And this equation is sufficient to describe the electron-phonon interactions in the material, ultimately that give rise to superconductivity in the material. So it looks a little complicated, but in reality, it's not that complicated. And it describes this material very well. And this equation can be used to abstract the superconductivity we observe, the material property in this compound niobium, or this element niobium. And I can abstract or transform niobium into lead. So I'm not doing any alchemy here, but the same set of equations, or this equation in particular, describes both niobium and lead. The only difference is there is a renormalization or a change in the coefficients that enter this expression, okay? But the underlying structure that governs the material properties is described by this equation. It's clearly nonlinear. And what remains to be determined is this mathematical formulation. So for me, when I think about designing materials, the key is to really arrive at a fundamental description of the materials mathematically. And in some level, we can then map, using an abstraction, this equation between these 2 different materials. And it's that concept, this abstraction, allows us to take a material with properties governed by a set of equations and transmute it into another compound with different properties. We're not really violating any laws of thermodynamics or the universe. We're simply saying that there is a mathematical structure that describes the behavior of a material, and there are coefficients or terms in that mathematical structure which can be defined and relate one material to another material. And that's how I think in some level about materials design to discover new compounds. So in this analogy that I've been trying to make for you, the abstract equation acts just like our numbers. And this, as I mentioned, doesn't violate any laws of nature. And for the materials that I'm going to talk about, or designing materials at the picoscale, where I want to focus on the electronic structure of materials, the governing equation that I want to use, or that is frequently used in my group, is not this gap equation for BCS theory, but rather what is known as Kohn-Sham density functional theory. And this is an expression for density functional theory, or DFT, in which you write the energy of the system or your material in terms of an effective potential, which knows how the atoms are arranged in the material, and as a function of the electron distribution, the kinetic energy and the potential energy between different electrons. And then there's another term, which is just a simple, let's say, fudge factor, which accounts for the approximation we make when we describe how electrons interact with other electrons. And this expression can be used then to abstract materials from one class to another class, as well as to describe material properties. And this is what we'll use then in terms of describing properties. So they, again, will arise from how units, these structural units of materials, are tiling space to create a crystal. And the electronic distribution will be governed by quantum mechanics. And we'll use these then to predict the properties of materials. So we'll use this abstraction thinking to design new materials which haven't yet been made in the laboratory before. And so the fundamental question we're asking constantly in my lab is this one. It's like, how do you start with a real microscopic model and obtain a real material? And at least for the REU students, you all take classes, you all derive models, in various formats. And then you're probably asking like, what's the relevance to what I'm doing? If it's in engineering or in chemistry or physics. And you can do, wave mechanics, quantum mechanics, just classical mechanics. And then it's like, well, what do I use this for? And so the challenge is always to make that translation from a microscopic model, which describes the behavior of a material, to identifying a new composition. This is the design or discovery challenge. And can I do that with targeted properties? So if an engineer or someone comes to you with design constraints, it has to operate under these temperatures or pressures, it needs to have this type of performance. How do I start with a very simple model and bridge that to something which can be made in the laboratory and then maybe translated to a commercial application? And so these are the questions we're thinking about in the group. And the argument is that we can focus on the models, do this abstraction, and that will help guide the materials design and discovery. So my group, I have a number of students in my group. Here's a picture of them. It's now outdated because I see everyone virtually. But there's a number of graduate students and postdocs who have contributed to this type of thinking and the projects we're working on. And what I want to do is tell you about this type of thinking in a very specific application, which is metal insulator transitions. And the work I'm going to tell you about was done by Lauren Walters, who's here. And she worked with Richard Ceballos, who's here, with an REU student in 2018. And that's what I'm going to tell you about next. So before I go to this specific example, I'll just pause again and see if anyone has any questions about this thinking of abstraction and design for materials. And you can argue with me if you believe materials are not abstractable like numbers, or you think they're more like faces. We can argue or discuss exhaustively about this, but hopefully it helps you start thinking about, when you want to find a new material or enhance the properties of a material or tune them in some way, how can I do that rationally, or how do I think about doing that? So if anyone has any questions, I'm happy to take them before moving on. Okay, so I'll keep going. So the next thing then that I want to touch base or set up is this concept of a metal insulator transition. And this is really what we're going to try to design in this process of using abstraction. So what I have in the upper left of this slide is a crystal structure. So this would be a compound which comprises octahedra. And in the projection I'm showing you, you can see that the octahedra share an edge. So they're connected together by an edge. And these edges are connected in one-dimensional chains. And so this material is quasi one-dimensional, even though it's a 3D crystal. Okay, and the specific material for which I'm showing the electrical resistivity as a function of temperature is vanadium dioxide, so VO2. And vanadium dioxide adopts this structure, and this structure type is known as rutile. And what's shown here, this is experimental data, as a function of temperature, just above room temperature, if you cool, say from 450 Kelvin, start cooling the material down, the resistivity decreases. And this is a signature for a metal. So if I take the slope of this curve in this vicinity, say d rho dt, the slope of this line would be negative. And that's what is an indication or allows us to classify a material as being a metal. And then at a finite temperature, just above room temperature, the resistivity jumps abruptly and it increases rapidly. And if I take the slope of this line, it would be positive. d rho dt would be greater than 0. And this is the signature of an insulator or a semiconductor. And so the compound, as a function of temperature, changes its conductivity class. At high temperature, it is a metal. It allows for electrons to freely flow in the material. And then below, say 350 Kelvin here, it acts like an electrical resistor. So it does not want electrons to flow through the material, and it's an insulator. So we would say this material undergoes a metal insulator transition. And this is a very functional aspect of the material. We've done nothing but apply temperature, and it can change its physical properties. And these types of transitions are being exploited and explored extensively today for new microelectronic devices, physics beyond that which can be obtained in standard CMOS devices. So things based on silicon, like your current laptop or mobile device. And these materials also have, or these devices also comprise materials which exhibit changes in electrical resistivity. But what is changing is the number of electrons in the material, or at least the number of electrons in the active region of your transistor. And typically you control that statically by doping. So you dope silicon with electrons or holes through phosphorus or boron type doping. And you can move electrons in and out. The material I just described to you can change its resistivity just like silicon and dope silicon CMOS based devices, but without doing any physical doping. And you can do it thermally, which I showed you on the previous slide, or you can do it electrically, just like you would in a microelectronic device. And so these types of materials are being sought after for replacements or complementary components to silicon CMOS. And it's being, in fact, implemented in a number of memory devices. In fact, it's implemented in Intel's Optane technology, which I show you just the schematic. This is a publicity schematic from them. Now, I guess it's 2 years old. But this is a multi-cross-point memory device with a high-density storage. And this component here, which is called a selector, operates on the principle I just showed you, that it can undergo a metal insulator transition without physical doping of the material. It simply is electrically activated rather than thermally activated. And in vanadium dioxide, the example I just showed you, you can electrically activate it as well as thermally activate it. And so there is intense industrial interest in these types of materials. And you can imagine, just considering the scope of the semiconductor technology market, sort of the immense interest financially in finding new materials in this domain. And so what we're looking for in this specific example is our, improved selector materials. And the fundamental aspect of the selector material is that it undergoes a metal insulator transition, okay? And what that means is that when I transition from the metallic state to the electrically insulating state, there should be a large change in the resistivity. And that's what this large on-off resistivity ratio is. And what I'm plotting for you in the upper right-hand corner of this slide is resistivity as a function of temperature for a number of materials. So things like vanadium dioxide, which I already mentioned to you. So this is the temperature at which that thermal transition from the metallic to insulating state would occur. So it's somewhere around 350, oops, let me go back, 350 for vanadium dioxide. For this material, niobium dioxide, which adopts the same structure, it's much, much higher temperature. And then the width of this bar tells you how large the change between the metallic state and the insulating state is. And really, for these types of devices, what we want are materials that operate at least around 100 C, so somewhere up here. And this resistivity ratio is very large, like 10 decades or 5 decades would be good. So something like a bit larger than what vanadium dioxide is. And there really aren't optimized materials in that space. And so this is the design challenge. We can start with what nature has given us, like vanadium dioxide, and then how do we improve upon it? And this is where the search, the materials search or the materials design comes from. So we can go back to our analogy with searching for Waldo and try to search by material structure and materials chemistry or composition. And what we'll do is first just focus on material structure and take the example of vanadium dioxide, the one I introduced this concept of metal insulator transitions for you. And the structure now is shown in a slightly different perspective. So instead of looking transverse to the chain, so you see those one-dimensional chains of octahedra, I'm looking down them. And so the chains are running into the plane of the screen that you're looking at. And this is the transition. In one phase, the material's insulating, again, at low temperature, and high temperature, it's metallic. There's a lot of details on the slide. The details don't really matter, but what happens across this thermal transition is that the insulating phase has a change in the structure. Grossly, it's the same, except for the fact that the vanadium atoms start to get closer and closer together. And in the tetragonal phase, the high temperature phase, this black one, the structure is metallic, and all of the vanadium atoms are equal distance from each other. If I take one of these chains, turn it on its end, you can see what happens. These two vanadium get closer together, and these two vanadium are further apart. So these two are closer together, these two are further apart, and these two are closer together. This is a type of distortion in the structure that's permitted by the one-dimensional chain of the rutile structure. So it's a very special rutile structure. And what happens then is that this vanadium decides to make a chemical bond with this vanadium, and they each share one electron. And this forms a singlet state, which maybe you heard of in chemistry before. And this material then becomes electrically insulating. When each electron is shared only by one vanadium, that's the character of the metallic state. And that's what occurs when every vanadium is an equal distance from another vanadium atom. And so this is the structure that gives rise to the metal insulator transition. And the structure can be adopted by many other transition metals. So vanadium is just one of them. I already mentioned niobium. All of the other elements on this slide or in this table can adopt the rutile-like structure, except the ones that have been grayed out. They're very difficult to make in the rutile structure. And here on the right is a table of the other physical properties that some of these materials can host. So it's a structure which is very flexible and it can accommodate a range of atomic and electronic structures. So some of them are metallic, some of them are semiconducting, some of them exhibit this transition. So it's within this family we've identified that we want to do this materials design. So some sort of abstraction, transforming vanadium dioxide into something else that might have an improved metal insulator transition characteristic. Okay, some of the details here don't really matter, but I just wanted to highlight the flexibility of this structure. So very few changes need to happen as I change, say, the size of the cations that accommodate or accommodated in this structure. So vanadium dioxide is the one I've been talking about, and vanadium has a particular radius, 0.58 angstroms. Ruthenium has a particular radius, 0.62. And what you can see is that in this rutile structure, when I make the substitution for vanadium with ruthenium, the major change in the structure is the C lattice constant, how long the lattice constant is along this direction, the unit cell. The A lattice constant, the one in plane here, doesn't change very much. It's fairly similar. The major change is the one along the out of plane direction. And so the structure is very flexible in that sense. And it's known, and here's sort of where the abstraction comes from, that this ratio, this length C over this length A, will dictate whether or not any of the materials in this rutile family can exhibit a structural transition and or a metal insulator transition. So there's a huge number of compounds on here. And I'm just going to move a little bit more quickly through this part. But what you can see is that as a function of C versus A, if you're in a range where the ratio C over A is large like this, all of the structures adopt the rutile structure, meaning the distance between metal atoms is equidistant everywhere. If you're below this magic line of C over A equals 0.625, that's what this red line is here, then the compounds prefer to adopt the distorted structure, the one in which you saw where vanadium pairs up and it forms pairs. And that can give rise or is conducive to then a metal insulator transition. And so what you want to do when designing this type of physical transition in this class of materials is you need to find a compound which lives somewhere along this line. And so that's the design challenge. So how do we get materials which live very close to this line? And if you look, niobium dioxide and vanadium dioxide are right there. And those are the two compounds in this family of rutile materials which exhibit the metal insulator transition. And so that's our design challenge. And so what we're going to do is not use cation substitution, but use a very alternative strategy, which leverages what are called heteroanic materials. And this is, in fact, the focus of IRG2 in the MRSEC at Northwestern, in which you're participating. And here we are looking at a whole range of compounds which have multiple anions. The ones I wanted to highlight for you in this talk are what are called oxynitrides, where you take oxygen and nitrogen and you make a transition metal compound out of them. And the reason you can do this is because the ionic radii of these two anions is fairly similar. And so they will form or can form compounds in which you have both anions or anions comprising both oxygen and nitrogen. And so this is the design challenge that I'm going to tell you about. So I'm keeping a track on the time. And what we want to do is combine then the chemistries that would be conducive to this metal insulator transition and make it compatible with the structure, the rutile structure. And we need to do one other thing, which I haven't really explained to you, but we need to make sure that the structure isn't so strongly favors, say, the monoclinic phase, the root distorted one versus the rutile one. Otherwise, we will only always live in one state. So if you remember back, vanadium dioxide was able to transition from one structure to the other. The ideal one, all the vanadium were equal distant, to the distorted one where some of the vanadium paired up and then paired up. So the structure needs to be flexible enough to go back and forth. If we choose chemistries which are so strongly destabilizing that the structure only always exists in one, we will never be able to activate the transition. So in some sense, having too much of a good thing is actually bad. We need to live in this sort of Goldilocks conundrum where we need something that's just right so we can switch back and forth between the two materials. And so we can formalize mathematically and maybe more physically what this requires then of the material. And what we will do is choose a compound. So we're going to start with this rutile-like compound. We need to have a particular electron count, and that leads us to select molybdenum 5+, which is D1. I already told you about the chain-like structure in rutile. This will give us that metal-metal bonding between the molybdenum atoms. And then we need to have a structural instability. And this is where the lattice parameters, or the ratio of those lattice parameters, is around 0.625. And so the way we'll do this in a multi-anion or a heteroanic material is to choose early transition metals, and we can choose oxygen and salt or sulfur. These are the same oxidation state, or fluorine or halides, fluorine and chlorine. And people have thought about doing this. There's a niobium oxyfluoride, which mimics this transition, and there's a titanium oxyfluoride, which mimics this transition. And so what I want to do or tell you about is the project where an RU student said, let's try nitrogen. And so he's looking at an oxynitride. And the idea is very simple. This table is now written sort of mathematically in a chemical formula where what we're going to do is take an oxide, molybdenum dioxide, combine it with molybdenum nitride, and what we get in the end is molybdenum oxynitride. And this will give me the electron count that's required to drive the metal insulator transition. And it should be compatible with this rutile structure. That's the hypothesis. And so to determine whether that's true and we can drive an electronic transition from a metal to an insulator requires some experiment. And so one could go do this in the laboratory, try to synthesize this material and make the electrical measurements. But our approach then is to use this framework of density functional theory that allows us to abstract the equations that describe molybdenum dioxide and molybdenum nitride and to use them for molybdenum oxynitride and explore in advance of synthesis whether or not this compound will exhibit a metal insulator transition. So that's what we've done. So we've done this calculation then for molybdenum oxynitride. And what I'm showing you now are some electronic structure results. So these are on the oxide component, so that first member in that chemical formula. And molybdenum dioxide, this is the electronic density of states as a function of energy. And so what I'm looking at is the distribution of electrons. And the light blue curve, the shaded one in the background, is the case for molybdenum oxynitride. And the Fermi level, so if I count all the electrons that are supposed to be here, the Fermi level is located in a band. And elementary band theory tells you that if you put the Fermi level in a band, meaning it's fractionally occupied, then you have a metal. And indeed, moly dioxide can be made and is a metal. And even if you distorted moly dioxide, that's what this dark blue curve is, the material remains metallic. The number of electrons at the Fermi level decreases, but it stays metallic. And that's because of fractional filling of this Eg pi state. So this is a local chemical description of the electronic structure, but we don't really need to discuss it in any detail. I can also look then, so this is the local orbital structure. If there's questions, I can answer them about this. But now we can look at the nitride end member. So this is moly nitride. And nominally moly nitride in the rutile structure is a semi-metal. So it has a very small number of states at the Fermi level. That's what's shown down here. And if you put in the monoclinic distortion, it prefers to have the monoclinic distortion, it will be insulating, as you would expect. So it has 0 d electrons and is basically a 0 gap or a small gap semiconductor. So these are the two end members. And then what we wanted to know is what happens if I make this heteroanalog, so molyoxynitride. And so this is the moon. So we're going to study the compound molyoxynitride. And this is the work, again, of an REU student from 2018. This is Nathan Szymanski, who's now pursuing a PhD in material science at UC Berkeley. Okay, and he's in his second year now. And the results of his work have been published last year, late last year, in Physical Review Letters. So if you want to see more details of the study, you can go to this journal article here. Okay, so what Nathan did was he basically asked the question, if I take this composition, molyoxynitride, is it going to be stable in the rutile-like structure? And what he did was searched exhaustively all possible AB2 or A2B structure types and found indeed that the lowest energy structures using density functional theory were these two prototypes, this technetium dioxide and this molyoxide-like moly dioxide structure. These are very similar to the monoclinic structure of VO2, which I showed you earlier. In fact, the structure of moly dioxide is indeed that one. And in addition, what he found is that the lowest energy configuration for the anions, remember this is a compound that not only has oxygen but nitrogen in it, is the one that's shown in this inset here, where the nitrogen prefer to share one face and the oxygen prefer to share one face. And if your background is in chemistry, this is in fact is called a FAC configuration of the octahedra compared to like a cis or trans configuration. And the FAC conformation is the one that's most stable for this molybdenum oxynitride. And he also did a series of density functional calculations to show that the alpha phase, as we'll call it, is on the convex hull. So this is the ground state structure of molyoxynitride. And then Nathan looked in more detail at the atomic structure. So the high temperature phase, in analogy to what I described for vanadium dioxide, is the beta phase here for molyoxynitride. And in this case, the blue atom, which you see here, is the molybdenum atom. And in this phase, the beta phase, the moly atoms are all equidistant from each other. And this is what we saw happened also in vanadium dioxide. And this structure is indeed metallic at the first principles level. Then there is a distortion that happens. So the structure is unstable to this in this phase. And the structure exhibits a dimerization where the cations, molybdenum, come closer together. And they form pairs, just like we saw in vanadium dioxide. So these two moly atoms get closer together. These two atoms moly atoms get closer together. And then they also can't a little bit. And this is a feature also seen in vanadium dioxide. And this material exhibits an electronic structure which is also then insulating. So we have two phases which are competing with each other. One is a metal and one is an insulator. And the tendency towards this insulating state is dependent on this FAC ordering. So there is a strong driving force for this FAC ordering. And it's this combination of the heteroanionic character having two anions, which makes molybdenum D1 that allows for the metal insulator transition in the compound. And so in the metallic phase, the beta phase, here's the density of states again as a function of energy. The Fermi level is at 0. It's this dashed line. You can see that the Fermi level cuts through a band which is, populated by or derived from the molybdenum D states. When this dimerization happens, that's shown in this chain direction on the left, the electronic structure reconstructs, a gap opens, and the Fermi level is found at the top of the valence band in this case, or the way it's been drawn, and we have a filled state. And this is the singlet state, which we saw occurred also in vanadium dioxide. So molyoxynitride is a candidate metal insulator transition compound, which mimics what we saw in vanadium dioxide. And here is a picture of the charge density. So this is the real space distribution of the charge in molybdenum oxynitride. And the molybdenum oxynitride phase, the beta phase, the high temperature phase, what you see is that the charge over some window is localized on every moly site. Okay, so every electron that is derived from that moly is basically confined within some sphere to that moly site. When you dimerize, or these moly atoms get closer together, those electrons tend to be shared between each other. And this is the formation of a covalent bond, or the signature of the singlet state. And this is what leads to electron localization that causes the hopping of electrons in the material, which would cause the transport to not occur. And so this is the character of the insulating state. Okay. And Nathan went into great detail to understand what is the driving force for this phase transition. And I'm just going to skip through some of these slides here. But what he identified was that the dimerization is derived from what's known as a soft phonon, in analogy to what happens in vanadium dioxide. So this is the first rutile-like heteroanik material, which really does mimic the physics of vanadium dioxide. And if you wanted to understand in more detail how this occurs, again, connecting changes in local structure, as I introduced in the beginning, to changes in electronic structure, here are the spaghetti plots, or the band dispersions for those that sequence of phase transitions. And we know how the two structures are connected, the beta phase and the alpha phase, via a dimerization and a twist. Instead of looking at the density of states, we can look at how these bands disperse in momentum space. And again, the Fermi level here is at 0. And what I'm looking at is the distribution of these states in the reciprocal lattice. And what we find is that the beta phase is a metal. You've already seen this in the density of states. And if I look from gamma to Y, I'm looking along the dimer direction in real space. If I look from gamma to E, I'm looking along the twist direction. So remember, these chains of moly atoms dimerize, but then they also can't a little bit. And both play an important role in the metal insulator transition. And with our first principles calculations, we can decouple them. This is something that's very difficult to do in the experiment because they occur simultaneously. But we can identify what is the contribution of each distortion locally to the macroscopic electronic structure, which is shown in this band dispersion on the right. So the details are on the left, but ultimately you see you need both combinations to lead to the gap that you see in the alpha phase. And this is then down here is the alpha phase, or the insulating state of moly oxynitride. Okay. And then Nathan did a final set of calculations to examine the effects of finite temperature on the stability of the material. And what we see is that there is a phase transition. This thermally driven metal insulator transition is going to be temperature dependent. So he monitored or computed the stability of that displacement as a function of temperature to track how this would thermally occur in an experiment. He did this with ab initio molecular dynamics. So he did a molecular dynamics calculation in which the forces are computed quantum mechanically to study the evolution. And then we also computed the formation free energies of the two competing phases. And what we are predicting is that this material would exhibit a phase transition somewhere around 900 Kelvin. So vanadium dioxide exhibited a phase transition around 350 Kelvin, niobium dioxide, so these are two oxides, exhibited a transition over 1,000 Kelvin. And this material, molybdenum oxynitride, is around 900 Kelvin. So this is the prediction. It's awaiting experimental validation, but we're working with several groups, both those at Northwestern and elsewhere, to try to confirm this electrical phase transition. And just based on the temperature scales, we expect and do know from our detailed electronic structure study that the mechanism here is much closer to that, in fact, of niobium dioxide. Really, it's driven by this structure instability, whereas in vanadium dioxide, it's driven in part more from electron-electron correlation effects. And so this is the advantage of using first principles methods in the design of materials. And so what I told you about is how I think a little bit about materials design, starting from the context or the point of material search, which you may have heard of from another speaker, or you have seen with high throughput electronic structure calculations. And the emphasis has been on abstraction. So once I have a physical model or expressions which allow me to abstract materials, I can then do design through chemical substitution and structure identification. And so what I described to you then was this case of a new novel metal insulator transition material, molyoxynitride. And so that's all I have for you guys that I wanted to share. And I'm happy to answer any more questions about the details of this study if you like, or any general questions if you have them.